This is section 6.5, the average value of a function, and our first and only content objective is to understand and use the mean value theorem for integrals. When we're done, I'd like you to be able to explain the relationship between the average value of a function and its antiderivative's average rate of change. Prior to this course, computing an average involved finding the sum of n items and then dividing the result by n. So your first exposure to calculus, to the concept of average, was in the context of average rate of change, or the secant slope on a given curve. Now we want to find the average value of the function itself rather than the average rate of change. So to develop this, we're going to backtrack to that old idea of average from our earlier mathematics courses and then connect it to our old friend, the Riemann sum. First of all, let's consider the curve f of x, for which we want to determine the average function value on the interval from a to b. We'll start by picking a sampling of n regularly spaced function values. So we have f of c sub 1, f of c sub 2, f of c sub 3, etc., 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 all the way up to f of c sub n. If we average these function values by dividing their sum by n, we would get the average of f of x equals the sum of f of c plus f of c sub 2 all the way up to f of c sub n, and we're going to divide by n. So here we've got this average, which is a sum of selected y coordinates divided by n, because we've got n of these coordinates. We want to connect it to the Riemann sum. So let's recall what that Riemann sum looks like. The Riemann sum, which we saw before we got to the integral, was a summation of f of c sub k times a delta x, where k started at 1 and went to n, and then we applied a limit to it and let n go to infinity. When that happened, we had an infinite number of slices, so that turned into our integral of f of x dx on the interval from a to b. So we want to somehow convert this into this. And looking here, we can see that we've got that sum of f of c sub k's already. What we're missing is that delta x. So let's recall that delta x is defined to be the length of the subinterval divided by n, and we've got this 1 over n right here. So if I isolate the 1 over n, I'll get delta x divided by b minus a is equal to 1 over n. So I can come back to here and write that average f of x is actually a delta x over a b minus a times the sum of all these y coordinates, which we can condense using our sigma notation into this. So if I now distribute this delta x to everything that's being summed up, that's the same as a 1 over b minus a times the summation of f of c sub k times delta x. Now the only thing remaining is to put a limit on it. And remember, we were trying to find the average function value. And currently we were adding up only n of those function values, when really we want to add up all of them and then divide by the total number that there are. Since there are an infinite number of them, we're going to add a limit as n goes to infinity onto that sigma. Now we have created that Riemann sum, and we can see that the average function value is actually 1 over b minus a times the integral from a to b of the function with respect to x. So graphically, what does that mean? Well, it means the average function value is the accumulation divided by the length of the interval. So if we think in terms of geometry, we can see that the length of the interval would be that b minus a, and the average function value is essentially the y coordinate, so that the length times the height gives us a value that is the same as the accumulation. So you can think of that b minus a as the width of the rectangle. The average function value is the height of the rectangle, whose area will now give you the same number as the accumulation of the function. This is summarized in our mean value theorem for integrals. It says if y equals f of x is a continuous function on the closed interval from a to b, then there must exist some point c such that the output of the function at c is the same as that average value. So the hypothesis of this theorem requires that f be continuous on the closed interval And as long as it's continuous on the closed interval, then we are guaranteed a function's output such that the output is the same as the average function value. Now what's interesting is that it has the same name. It's this mean value theorem. So it's got to somehow be connected to the mean value theorem we learned much earlier. And let's see what that connection is. Let's consider a continuous differentiable function capital F of x and its continuous derivative capital F prime or little f of x. The mean value theorem for integrals applied to little f guarantees a value of c in the open interval for which the output of the function, the output of little f, is the same as that average value, while the mean value theorem applied to capital F is going to guarantee a value of c in the open interval for which capital F's derivative or tangent slope is the same as the secant slope for the endpoints of the interval. So somehow, since they got the same name, they should have a connection. So if we look here, we have little f of c equals this, and we have big F prime of c equals this. Well, let's recall that this is a question in disguise. This says, what did I take the derivative of with respect to x that gave me little f? And we know that we took capital F's derivative to get little f. So we could use the fundamental theorem of calculus to answer the question and say, we took the derivative of capital F, and then we can evaluate it from a to b. That will give us capital F of b minus capital F of a, and then we're multiplying that by b minus a. Notice that that is the same as this. Notice too that if I take the derivative of capital F and evaluate at c, I get the same thing as little f evaluated at c. So all four of these are equal to each other. If you look here, you can see that we have a specific example where capital F is x cubed minus 2x squared minus x, and its derivative, which is little f, is 3x squared minus 4x minus 1. I've graphed both little f and capital F on the interval from -1 to 2.5. Now we can see graphically that the average function value, which is 1 over 2.5 minus a -1 divided by the integral from -1 to 2.5 of little f, is going to be 0.75. And on the big F's graph, we can see that that secant slope is also 0.75. And it turns out that the c values, the places where the secant slope and the tangent slope are the same, which should be here and here, are the same places where the height of little f, or the output, is the same as the average function value. So not only are the theorems equivalent, but the values of c that you find from both are the same. So let's look at example 1 and see it in action. Let's find the average value of f of x equals x cubed minus 1 on the interval from -2 to 4. Well, we write down that the average of any function f will be 1 over the interval, which is 4 minus -2 times the integral from -2 to 4 on the function we want the average of. So one thing that trips people up is they ignore what it is that we're getting the average of. If I want the average temperature, I need to put the temperature inside here. If I want the average weight, I will put the weight inside the integral. If I want the average rate of change, then I would put a rate of change inside the integral. So that's going to be a little tricky because you're going to want to do different things when you see words like average rate of change. So here I've got this. If I simplify it, I'll have a 1 over 6. This asks the question, what did I take the derivative of with respect to x that gave me x cubed minus 1? And the answer is x to the 4th over 4 minus x. And I'm evaluating from -2 to 4. So plug in your 4. You'll get a 4 cubed minus a 4. Plug in your -2, you'll get a 16 over 4, which is a 4, minus a -2. So it looks like we have a 60 minus a 6. That's a 54 divided by 6 gives us 9. With example 2, we want to find the average value of the function shown below without using antiderivatives. So we write down the average function value will be 1 over the length of the interval, which is 1 over 4 minus a -2, times the integral from -2 to 4 of the function. Now, because we aren't using antiderivatives, that means we need to compute this accumulation by hand. So we'll have 1 over 6, and then we'll look at the accumulation and equate it to area. We can see here that we have a quarter of a circle, so this would be a 1/4 pi times the radius squared. We can see that we have a rectangle that is 2 by 4, so that'll give us 8, and then we have a triangle whose base is 4 and whose height is 2. So this one would be a 1/2 times a 4 times a 2. So it looks like we have a 12 plus a pi. So our average function value will be 12 plus pi over 6. With example 3, we have a cup of coffee with an initial temperature of 95 degrees Celsius put in a room where the temperature is 20 degrees Celsius. Then, according to Newton's law of cooling, the temperature of the coffee after t minutes will be given by this. The question is, what is the average temperature of the coffee during the first half hour? So since time is measured in minutes, we need that half hour to be a time interval measured in minutes. So we can say that the average temperature will be 1 over the 30-minute period, so 1 over 30 minus 0, times the integral from 0 to 30 of the thing we want the average of. We want the average of the temperature, so that means we will be integrating this 20 plus 75 e to the negative t over 50 with respect to t. So put that in your calculator and you will end up with 76.399 degrees Celsius. Now I want to take just a minute to talk about the units, because here we had minutes on the bottom, and if I'm collecting temperature, which is degrees Celsius, if I integrate this, then that accumulation is going to be the height times the width, which is degrees centigrade times minute, and then notice that I'm dividing by minutes. So the minutes cancel and I end up with just degrees Celsius, which makes sense. The average temperature should be measured in degrees. With example 4, we are given a numerical example and asked to find the average value using the midpoint rule. So first we'll write down that the average function value will be 1 over b minus a times the integral from a to b of the function. Now, if we knew what the function was, we could answer the question posed by the symbol, what did we take the derivative of with respect to x that gives us little f? But because we don't, our only recourse is to estimate it using one of our approximation methods. In this case, since we want a midpoint rule, we need to select subintervals that actually will generate middle x values. So we can see that if I choose subintervals that are 10 units wide, then we'll have middle x values that will then in turn have middle y values. So we can approximate the accumulation by doing the width of 10 and the heights of 38, 29, and 48. Put that all together on your calculators and you will end up with 38.333. For our fifth and final example, we are shown the velocity of an accelerating car that's measured in meters per second in this graph. And the first question is, we want to estimate the average velocity of the car. So we know that the average velocity should be 1 over the length of the interval, which is 12 minus 0, times the integral from 0 to 12 of the thing we want the average of. So we want the average velocity. Now the reason we're told to estimate is that we cannot answer the question posed by the symbol because all we have is a picture. So what they're really asking us to do is to estimate this accumulation. So we've got to think about what this accumulation will be. And there are a variety of methods we could use. We could do LRAM, RRAM, MRAM, or we could just simply count and kind of do a ballpark estimate. So I can see here that this is shaped an awful lot like a triangle, and the triangle has a width of 12 and a height of, it looks like, 70, and then we've got some more of these. So I'd say this is probably 1, maybe 2, 3, 4, 5, 6, 7, 8-ish, plus 8 more of those, and each one of those is worth 10. So we've got 6 times 70, that's 420, plus 80 looks like we have about 500. So we're going to take that 500 and divide it by 12. That will give us about 41.6 repeating, and since we estimated, let's say that that's about 42. Now the question is, at what time was the instantaneous velocity equal to the average velocity? So that's asking us to figure out when outputs on this graph actually equal that average velocity of 42. So if we look at 42 and go over to the graph, it looks like it happens at about 5 seconds.